Hello, everyone.
Hello.
Hello.
Good afternoon.
Hi.
Good afternoon.
So before
Hi.
Baba starts, I just want to, well, thank you all first for being here. And we have three presentations today. I think we're lucky to have three of our, teams available today to give us updates about their ongoing research from three different universities in the center. That's great. Of course, the Associate Director from Louisiana State University, Professor Bhaba Sarker, will be moderating the session today, or the webinar today. I just wanted to say a few quick announcements for those probably who have received the RFP for year 2. I hope you all received it. And we'll be holding soon a meeting with the Associate Directors to discuss the RFP, and so they can, communicate the information with their with the respective faculty members from their institutions. I just wanted to bring this up a little bit before we go ahead with our webinar. With that being said, I'll just like to pass it over to Baba. Baba, go ahead, please.
Okay. Good afternoon, everybody. As I heard, I'm Bhaba Sarker with Louisiana State University. There are three presenters today. Me and my co-author Anik Mazumder from LSU, and the other one is from Pranay Singh from University of Buffalo, and the third one is by Professor Jacob Hansen from University of Illinois at Urbana-Champaign. I am right now located at Ann Arbor, Michigan, and my other author is at LSU, and he will be presenting from there. And the topic is optimizing pallet capacity utilization to minimize the curing cost in precast concrete manufacturing. Mr. Anik Mazumder joined our program last January from Bangladesh University of Engineering and Technology. He is pursuing dual degree, both master's and PhD in industrial engineering, and his area of research in basically optimization applied to now civil engineering applications. So with it as introduction, he is just here, even not one year yet. So he will be presenting some of the progress that he has completed in the project. So here I switch over to Mr. Anik Mazumder from LSU. Anik?
Am I audible?
Yes.
Yes.
So I'm just trying to share my screen. Is my screen visible?
Yes.
Good evening, everyone. I am Anik Mazumder with Dr. Bhaba Sarker. We will now represent our research work in our phase 2 progress that will be on optimizing pallet capacity utilization to minimizing curing cost in precast concrete manufacturing. We are from Mechanical and Industrial Engineering from Louisiana State University. This will be our outline for the total presentation. We will first introduce our problem, and then we'll move into the explanation that what is our existing problem. Then we will approach to the model development. Then we will apply an example to that using that model. We will then analyze the computational results and the computational performance of our model. Then we will explain our future works following by the application and scope. Then we will talk about our working papers following by the references. To introduce, precast concrete refers to concrete components that are molded and cured in controlled manufacturing environment before being transported to the construction site. Common components related to transportation infrastructures include bridge beams, pavement slabs, road slabs, columns, and other structural elements. There are too much benefits for this using the uses of precast concrete in the construction of transportation or infrastructure because they are providing consistent quality as they are manufactured in a controlled environment and ensuring the uniformity and high standards. Their efficient installation is ensured because precast components can quickly be assembled on site, reducing construction time, and then it can accelerate the construction process. If we just take a look about our working in our phase one, in our phase one, we aim to develop a hierarchy framework of significant factors representing the interdependencies or relationships of precast concrete supply system using interpretive structural modeling. At first, we identified the factors associated with cost, reliability, and sustainability. Then we explored the interdependencies or relationships in each element. Then we have developed a hierarchical framework which helped us to develop this CCM model or curing cost minimization model. So this was the hierarchical framework that represents the relationships among all the factors that are related to cost, reliability, and sustainability in the precast concrete manufacturing sector. This dashed line indicates the indirect relationships, while the solid arrows indicate the direct links to each factor. A factor positioned at an elevated level signifies its capacity to impact a greater number of other factors. For example, if we take QC, which is quality control, we can identify the factors on which QC is spatially or highly dependent, such as it can be CC or cement content, WC, that is water cement ratio, and CCR, chloride and carbonation resistance, and so many other factors. Now, if we talk about the motivation of our research work in this phase 2, we need to know the importance of efficient production of precast concrete. If we talk about the transportation infrastructures, it is essential for economic growth and connectivity, such as roads, bridges, and urban transit systems. And also, it is very critical for maintaining project schedule and budgets. Also, we can face some production challenges because it plays a significant role on cost and efficiency due to the mold setting and curing process. And also, it can be high energy consumable and can create a high amount of labor cost. Several studies have addressed various computational techniques that can address the planning issues and also that can aim to reduce the cost and project completion times. According to Zhou, they proposed a heuristic approach for the job scheduling. According to Chen and Hu, they developed a genetic algorithm for flow shop sequencing. According to Prata, they proposed an integer linear programming model which aimed to schedule the production of beams and also to minimize the empty spaces in the molds. And also, according to Wang et al., they developed a heuristic approach to solve a suboptimal model to configure pallet layout during operations. So if we try to find out the research gap, there are limited focus on specific optimization process, such as how the components will be arranged in a batch or pallet for being cured, and how many batches or pallets will be required for the total curing process. Also, traditional models often assume the static conditions, and they are assumed that there is no variability in demand and deadlines. So what is our existing problem? In the most of the cases, a single component is placed in a single batch or pallet during the curing chamber, which can cause a high number of batches or cycles to fulfill the total curing operations. And also, it can cause us miss out the delivery deadlines and can create extra penalties. So we need an optimal strategy for placement of curing materials or components. So our basic research goal will be to minimize the curing cost by maximizing the average utilization of pallet capacity. And our objective will be develop a new plan for optimal layout configuration to arrange PC components on pallets and also to minimize batch or pallet cycles required during the curing process. For the formulation of the curing cost minimization, in short, CCM model will be used these kind of indices and system constances. And finally, we'll try to figure out the value of our system variables, or in other words, decision variables, that will be xj, that is the number of batches using a specific layout, and aij, that will represent the number of components that are present in that kind of layout configurations. And using the previous slides notations, we have developed the total energy cost. We will calculate the total energy cost for the PC components that is indicated in that is presented in these equations. And after that, we just have multiplied that with the total batch numbers. And also, we have calculated the cost of loading and unloading components in all the pallets. And by using that, we have developed our first objective function in our CCM model using the system variables, that is xj, the optimal number of pallets, and aij, a set of components of per pallets to minimize the cost of curing operations. So the objective function CCM in equation 1 represents the total associated cost of energy cost and the labor cost per component, and this equation will be minimized to find out the minimum curing cost. And this objective function was constrained by using some equations. The first equation will represent the total area of precast concrete components will be less than the pallet area. This second equation constrains that the second constraint represents that the total number of required component type I must meet the order agreement. The third constraint ensures that the production scheduling complies with the delivery deadlines of precast concrete components. The fourth constraint will indicate that length of precast concrete components having the maximum span are less than the diagonal of the pallet or the batch that will be present in the curing chamber. And finally, the equation 1e represents the decision variables. And that is the total package of our CCM model, having the observing function in 1 and other constants from 1a to 1e. After that, we have taken some example data as our example to verify our model, and we have taken various data like the pallet dimension and the precast concrete component dimensions to verify our CCM model. And using the data table 1, the CCM problem was numerically formed as follows. And then we have find out the optimal number of pallets for 2 types of specific layout configurations. And for the first layout configurations, we have figure out the x1 value, which is 2. And for the second types of layout configurations, we have found out the x2 value as 3. So the pallets component assignment matrix A is equal to aij is 2, 3, 1 and 2, 2, 1. And this actually indicates the number of each type of components placed in each type of layout configurations. And following this, we have determined the minimum curing cost, which will be $666 in a batch. And the computation input data and the output results are provided in table 2, wherein only the changed values are provided in the input data column and the rest of the parametric values are chosen from the table 1. This this table was built to just analyze the computational performance of our CCM model. And from the research perspective, the computational performance results were analyzed and found out the following points. When the demand DI per precast concrete components increases, the curing cost also increases as well as the computational time. When the length and width of the precast concrete components, I mean the dimensions, in other words, increases, the curing cost and CPU time also increases, but at comparatively lower rate. And if more components are assigned on the pallet or batch, fewer pallets or batch cycle are needed. And so the batch sizes leads to the lesser cost according to the third row of our table 2 in our previous slide. So in our future work, this mathematical model will be used to incorporate industry data in collaboration of Louisiana's Transportation Research Center. With increasing demand and dimensions of precast components, CPU time also get increased. So a heuristic approach will also be followed to get the optimal layout configuration to reduce the curing cost. The model will be revised to focus on the most critical variables that can reduce curing cost. And as our expected progress in phase 3, a supply network representation of the supply activities with their corresponding variables will be developed. A price volatility of precast concrete materials will be incorporated in the supply logistic problem. a model will be developed to determine the optimal process path that will minimize the expected precast concrete supply system's cost and improve the reliability and sustainability of the system. As an application and scope, this optimization ensures that each component is evenly cured, which is vital for the consistent material strength and the structural integrity. The economic efficiency achieved through the model not only lowers the initial project cost, but also reduces the life cycle expenses associated with the maintenance and repairs, supporting long-term sustainability. So these are our two working papers that we are working on. The first paper was to develop an interpretive structural modeling on factors, and that was the outcome of our quarterly progress report 1. And now we are working on optimizing the pallet capacity utilization to minimize the curing cost. That will be based on the outcome of the curing quarterly progress report 2. And these are the references to present this slide. And thank you, everyone. If you have any questions, please feel free to ask.
Any question?
I have a question.
Okay, yeah.
Go ahead.
So, Anik, thank you very much for very comprehensive, nicely presented work. My name is Jan Oleg. I'm from Purdue University, and I got a question related to the statement that the curing cost increases with the demand. Could you elaborate a little bit more why that would be the case? Because from the concrete point of view, there's optimal curing conditions, and it should be independent on the demand, right? I mean, there's not much you can do in order to accelerate if you are already accelerating. So, but maybe I'm missing something there. So if you could elaborate, that would be good.
This statement?
Yes.
Okay. So basically, this DI represents the demand for specific type of components that is indicated at I. So when the demands will be higher, like if you are dealing with two types of precast concrete components, one could be slabs and one could be beams. When the demands of slab is 40 and the beam will be 30, then there will be a specific kind of curing cost. But when your demand will be higher, then I mean, instead of 40, if it is 60, then you will have to pay for the curing cost, because you have your pallet cycle, or you will need the higher number of batches to cure your concrete, because pallet sizes is constant. You can modify the pallet or curing chamber, the dimensions of this curing chamber in middle of your operations. So yes, you will have to use that one chamber for all the curing all the components. So your curing cost will increase as well.
Okay, I understand. Thank you. So you basically have to adapt the curing to the demand, and that may not be the optimized process for curing, let's say, multi-elements of different types. Yeah. Okay. Thank you.
Any other question?
I think I might have it one question. Thank you, Anik, so much for the very nice presentation. You mentioned, you throw in some dollar amounts, and that all obviously brings the curiosity of somebody, from the industry to maybe ask the question, where did you obtain your main, dollar amounts that you have the cost? For example, you mentioned energy and labor as two main sources for the cost. When we say energy, I mean, do we know if the energy consumed by different precasters for the same type of component is the same? Are you taking this variability into account or not? Another important thing is the mix itself. I mean, when we say concrete, it's just one thing, but what goes into the concrete and the curing process? When you say curing, there's different components in the curing process itself that sometimes different precasters, adapt in their practice. So can you a little bit elaborate on the variabilities and how they are being included in your study?
Okay, so let me get back to the slide. You are talking about these two types of equations, right? Like in the... Right. Okay. So actually, in that equations, it is actually indicating the energy cost. Here, E is, if I just go back to the notations, then... Okay. So here E, we have calculated, indicated E as the energy consumption rate per curing chamber, and that will be in kilowatt per hour. And the CE will be the unit cost of the energy. So yeah, you have pointed out a very good point, because every precasters can use their curing chamber as in a different way. So they can use any kind of energy rate, and any kind of and unit cost of energy will be obviously vary from one place to another. So that will be actually based on hours, that for how many hours you are using that curing chamber for different types of precast concrete components. And that actually goes for the labor cost as well, because this labor cost is actually calculated by per component. Like when you will placing the component in the pallets or batch in the curing chamber, then the number can be different. So you will have to pay for that different value for each of the components.
About the material mix, and Baba, if you want to add something, of course.
Yeah, I think Basam wanted to know, when you have multiple components of different variety, then individual component consume different power. But in this case, Anik was doing what he was doing. He was basically measuring the power or energy consumed by the whole system, not by individual components, because then the layout will be differently arranged. But he took the combination of different one, but the time span for all the product remains the same, because the kiln chamber time is given on a batch basis, not individual component basis. It is measured on the batch basis. How much time, how much energy is consumed per batch, not per component. Am I clear?
How would the material, the mix itself of the concrete, and for example, the type of cement used and other factors, how does this play a role there, or if any?
Can you please repeat? There is an internet connection.
I was saying again, how would the mix components itself, for example, the type of cement used, how would this play a role in this whole process, if at all it plays anything?
Okay. To be honest, we haven't considered any kind of factors, like you have said, that type of cement or type of cement mixture in our model. But we will look about, because we haven't collaborated with any other industry yet. So when we will collaborate with them, then we will look about them, and we'll try to figure out that if they use different kind of curing operations or different types of cement mixtures or type of cements, because there are 5 types of cements, and concrete can be made of each type of cement. So we'll have to figure out by collaborating with them, and then we can use them as a variable or factor in our CCM model.
So there's plans to collaborate with the industry partners on this project?
We are looking at it. We couldn't fix up yet. Okay. We are communicating with them. Okay, but you raised a very good point, which I never thought of, but that will be a good point which we would like to add it to it. Thank you.
All right, thanks.
Go ahead. Any other question?
Yeah, just a follow-up question. Does the framework you presented has a manufacturing data? Because every manufacturer is different. Production rates, the type of frames, type of forms they use, the environment that they have. So does your framework have a manufacturing dependent data that I can account for?
Actually, this framework was developed on basis of the from some expert opinions and all the existing literatures, because it actually basically representing how each factor is related to another one. Like if you want to for example, if you want to increase the quality of your concrete, then quality is actually itself is a vague term. It is actually dependent on very other terms. So you have to look about what factors to improve your quality. And we just have figured out this kind of relations, because if you look at quality, then you have to look about your cement concrete or W/C ratio or CCR. So then, and so many factors. So we have basically figured out this type of things. But yes, we will try to figure out some numerical values and we will assign these values with something because there is a issue with reliability. So we still don't know that if we improve the W/C by 90%, then what will be the quality improvement ratio? So we'll try to figure out this data from the industries, and then we'll try to implement them in this framework. Thank you for that. Was a very good point.
Thank you.
Samir, I think your point is will be more elaborated. This data does not represent any particular company. It is just a representative data, but it will from company to company, from film design, chamber design perspective, the data will be different for different chambers. So we cannot say this is the generalized data for all chambers.
Good, I understand, but at least the model has a piece that can account for variabilities between
Yes.
manufacturers.
Yes.
Okay, that's the important part. Thank you.
Okay, I think we can, unless if there is any question, we can proceed to the next one. I assume no questions. So our second paper is 3D printed advanced materials to mitigate a pre-stressed concrete girder end cracks by Pranay Singh from University of Buffalo. He is in the Department of Civil Engineering, Civil Structure and Environmental Engineering. I assume he is doing a PhD. Let's hear from him rather than expanding on the title myself. Okay.
Hello everyone. Can you hear me? Can you see the slides?
Yes.
Yeah, so I'm Pranay Singh from University at Buffalo, and I will be presenting our research project titled 3D printed advanced materials to mitigate pre-stressed concrete girder end cracks. So the motivation for the project arises from a potential risk of end zone cracking in precast pre-stressed concrete bridge girders. And the problem arises due to transfer of large pre-stressing forces in a very short distance and low tensile strain capacity of the conventional concrete that is used in making these girders. So the solution that we are exploring is to use a 3D printed ductile concrete cell with better tensile strain capacity and crack resistance abilities at the end zone to limit the surface cracking. So the cracks that are exposed to the environment, we are trying to reduce the width of those cracks at the end zones. Considering our problem statement, the objectives we have underlined is to investigate the SSCC covers and how they can be implemented to solve this problem, and to develop a 3D printable strain hardening cementitious composite mix and a printing system to test to have the material level testing. Also, we are trying to look into the composite behavior of the SSCC and the conventional concrete, how they behave when they are casted together or formed together. As the technology will mature, it could have a lot of different kind of use cases and implementation. But at this stage, we are considering one simple method of implementing this, and this will have two different stages. So the first stage will involve 3D printing of these covers. So a 3D printed SSCC cover will be made either at the precasters facility or at any 3D printing laboratory. And once it is printed, it will be cured and given time to gain the strength. When it is ready, it will be transported to the precasters facility where they will have a pre-stressing bed and usual form works that they use to create these precast girders. And one of the feature of these 3D printed cells will be its thickness will be limited to the cover zone thickness of these girders so that it can fit inside the formwork without any modification. And then, as usual, non-pre-stressed reinforcement can be placed, and pre-stressing strands as well as the pre-stressing can be applied, and then the concrete can be poured. Once it attains its strength, the pre-stress can be released and the formworks can be removed. And what we will get is a composite bridge girder with SSCC covers at the ends. So this is one of the proposed implementation methodology that we are exploring. Coming to the strain hardening cementitious composite, so the material that we are proposing for the application is a kind of fiber reinforced concrete, which is optimized to have distributed cracking instead of larger cracks. So the constituents are basically the same as any fiber reinforced concrete, and the two ingredients, primarily the viscosity modifying admixture and high range water reducing admixture, that the ratio of these ingredients and the amount of these ingredients will be calibrated to achieve the 3D printability in strain hardening cementitious composites. So coming to the requirements for the mix that we are trying to develop, so it will basically have two different set of requirements. The first one will be the rheological requirement to make it possible to 3D print this kind of concrete, and the second one will be the mechanical requirement to actually fulfill the objectives that we have with these kind of cells. So the mechanical properties, one of the crucial one is the tensile strain capacity for a strain hardening cementitious composites. And how we are trying to achieve both these objectives is through iterative modification. So we started with a base strain hardening cementitious composite mix that is of course non-printable. It was developed earlier in our lab, and it has that strain hardening behavior. We are modifying its ingredient and changing the proportion of the ingredient in a way that the strain hardening behavior is retained, and it additionally achieves that rheological behavior to make it possible to 3D print. For understanding the hardened property objectives that we will need, particularly the strain hardening capacity of these materials that we will need from these kind of mixes, we developed a numerical model. So this is a 3-dimensional nonlinear finite element model, and we actually model a girder which was experimentally tested at University of Texas, and they got very wide cracks. So they had significant cracks at the end, and that's why it represents one of the worst cases of end zone cracking. So we modeled the same girder with the conventional concrete, and then modified it with SSCC at the ends. So when we did the numerical simulation, we obtained that the maximum strain that is reached on the cover surface is somewhere at 0.32%. And this marks the limit for the strain capacity that we will want to have with our covers. So as we can see in the stress strain plot, a conventional concrete will actually get significant cracks at this strain level. However, the strain hardening cementitious composites, they have the ability to sustain this kind of strain, and the average crack width, even at this strain level, will be somewhere less than 0.1 millimeter. The rheological requirements were established through a series of experimental investigation, and we observed that for strain hardening cementitious composites, they have different rheological requirements which are contrasting from each other for each stage of the processing. So we start with the mixing, and at that stage, fiber dispersion is crucial for achieving the strain hardening behavior. And then at pumping through our extruder and pumping through the tube, it have different rheological requirement. And later on, for buildability and extrusion and buildability, we have some different viscosity and rheological requirements. So how we achieved it through calibrating the two ingredients, VMA and HRWRA, and later adding some more ingredients that I will discuss in upcoming slides. So the first stage was viscosity modification. So from the base mix, we created 16 different mixes with different VMA to HRWRA content. And out of these 16 mixes, we tested them, and we disqualified the mix that were not showing the printability or water segregation or fiber dispersion. So we have discussed it in detail in our previous April workshop, and I will not spend much time on that. Once we filtered out the mixes that were not printable out of these 16 mixes, the selected mixes were further optimized for their thixotropic enhancement by addition of the ingredients like ground silica, microsilica, and type 3 cement. So eventually, after this rheological optimization, we obtained 3 mixes that were printable, and they had fibers in them. They started from our base SSCC mix. So now we tested these 3 selected mixes for its hardened property. So the mixes were mix 9 with inert silica, mix 9 with micro silica, and mix 10 without any additional ingredients. So we tested it at 28 days of ambient curing. Additionally, we are also developing a accelerated curing protocol for these mixes so that these cells can be made much faster whenever we are implementing it, as well as when we are testing it or developing it, we can iterate much faster to get our to fulfill our objectives. So these are the results. So I would like to discuss about the accelerated curing as well. So accelerated curing is actually a elevated temperature curing, where we elevate the temperature for about 5 days, and for the rest of the time it is in ambient curing. So it takes total 8 days. It is still in study, and we have not completely tested all the properties and compared that it is good, but we are working in that aspect as well. So the compressive strength result shows that for all of the mixes that we are trying, we are getting a compressive strength in the range of around 7 to 8 KSI, and our initial target was 6 KSI for all these mixes. So we are getting the desirable compressive strength for all the 3 mixes. The tensile strength of these mixes are somewhere in the range of 0.7 to 0.9 KSI. And the tensile strain capacity were higher than the limit of 0.4%. So we are getting somewhere in the range of 0.6 to 0.9 KSI on an average. We have done 4-point bend test, and the modulus of rupture from that 4-point bend test is in the range of 1.5 KSI for all the 3 mixes. And in summary, if we conclude the hardened property testing and the flow criteria that we wanted to fulfill from the mix, so all the 3 mixes has average flowability factor that is calculated from the drop table test we discussed in previous workshop. So it was in the range of 1.2 to 1.5, and that limit is actually what we found to be suitable for 3D printing purposes. The flow evaluation should be greater than 15%, and our mixes had that fulfill that criteria as well. The compressive strength criteria and tensile strength criteria are also fulfilled from all the 3 mixes. Next, I would like to discuss about the development of 3D concrete printer at UB. So 3D concrete printing has an aspect of machine material interaction. So the behavior of the material depends on the type of equipment that we are using and the setup that we have. So for that reason, we have developed our own concrete extrusion system, the control system, and a computer numerically controlled frame. So this computer numerically frame is actually a pre-built frame for plastics, for printing plastic, but we have modified it to work with concrete. And the control system that we are using is actually an Octopus board with Merlin firmware. And we input the G-code files for the 3D model through Pronterface, which is an open source software. And our control board controls the nozzle X, Y, and Z coordinate. And it has capability to control the feed rate from the concrete extruder. We have not yet done that. We are working with a constant feed rate pump, but later on we would include these capabilities as well. So one of the findings from the initial 3D printing trial is that the mix that we had developed requires some initial calibration for the feed rate, that is the speed of the nozzle and the motion of the jet direction. So what you are seeing here on the left is under extrusion, where we have assumed our extrusion rate to be higher than the actual extrusion rate. And on the right, you can see the over extrusion, where our assumed rate is less than the extrusion rate, causing some kind of scraping. So once we optimize this for a mix, for a particular mix, what we get is this kind of 3D printing, which is good in themselves. And here you can see that our focus is on printing the cellular structures with either 1 or 2 filament thickness. Although we can print the solid parts as well, But since our study is based on printing of the cellular structures or cells, our focus is on printing these cells and testing its properties. So what we're currently working on is printing different kind of cells and look at the 3D printing as well as their hardened properties. And we are also looking at printing some complexes like grouped cells to improve the behavior or the bonding between the concrete and these cells. So this all constitute our future scope of work. But this is the direction in which we are moving for 3D printing. So in summary, we established the performance requirement in terms of tensile strain capacity for our strain hardening cementitious composites, and it was found to be greater than 0.4%. We did some experimental investigation to come up with rheological requirement using drop table test, and we obtained the flowability factor that is suitable to be around 1.2 to 1.5 and flow reduction to be greater than 15% per hour. We performed hardened property test as well and found that the mixes were complying with the requirements. We further developed a 3D concrete printer with extrusion system CNC frame and a control system. So for future work, we are trying to investigate the bonding of the 3D printable SSCC with conventional concrete and crack resistance of the composite conventional concrete beam with 3D printed SSCC cover. So what we are trying to do is to test this idea of using SSCC, 3D printed SSCC as a permanent formwork in beam. So what we will do, we will take a usual formwork and put SSCC inside it, put the reinforcement, and then we will create some kind of composite beam to test the hypothesis that we wanted to propose later on for a real full-scale girder. So these are the references for the presentation. The findings in the study are being disseminated at different seminars and conferences. So we had presented this idea of using covers at TRB annual meeting in Washington. In September, we will be presenting it at 11th International Symposium on Fiber Reinforced Concrete. And later at TRB conference on additive manufacturing and construction in transportation, we will be presenting it at Irvine, California. We gratefully acknowledge the support from Department of Transportation, TRANS-IPIC, and Institute of Bridge Engineering at University at Buffalo. And we give a special appreciation to all our MS and undergrad students who helped us in various stages of the project. We also show appreciation to our lab staff who are helping us in conducting all the experimentation. This ends my presentation. Now you can ask your questions. Thank you.
Any question to Pranay?
Yeah, I can start with a question. Great work, Pranay. This is the second time I listened to a presentation, and it brings me in one question I have this time. So you are introducing a shell that's made from 3D printing concrete at the girder ends to prevent or to brace that portion from the cracks that propagates from the huge transfer loads from the girder to the columns. Correct? So you are bracing that side of the girder, correct?
Yes.
Should this problem be solved through revising the concrete mix design that account for these additional stresses across the whole girder, or shall be addressed by maybe expanding the size of the end girders with a larger size? So maybe try to resolve it instead of adding braces through a stronger mix design, or maybe a better cement for the concrete, or expanding the size structurally, so material or structurally. Would that be also an options that can be considered?
Yes, you
So,
are.
hold on,
Yep.
Pranay,
Yep.
just to go back to Samir's previous question. So this is not for transferring the load that is coming from the columns. It is just the it is just after the moment you release the pre-stress from the pre-stressing strands. So the girder is still in your precast plant, and the moment you release all that pre-tension load from the strands, it is transferred onto the concrete. And because of that, the transfer distance is very short typically. And because of that, the concrete has limited tensile strain capacity, and this end cracking develops even before the girder is taken out of the of your pre-stressing bed sometimes. So that is the cracking that we are addressing, not the cracking that is coming onto the overall structure of the beam. Yes, now go ahead, Pranay.
Yes, so regarding that, to control these cracks, there are various methods. The first one is the enhanced reinforcement at the ends. So we can do that. The second one is using better mix, like using fiber reinforced concrete or ultra high performance concrete for the entire ends. So these are some of the methods, and there are literature on them. People have used that, but those methods still have some problems. There is even with fulfilling all those criteria of reinforcement at the end zone, people have observed the cracks. Applying the fiber reinforced concrete for the entire girder, it will be expensive as well as difficult to do, because first of all, handling the fiber reinforced concrete is difficult than conventional concrete. It is expensive. And if we want to just make the end zone with those fiber reinforced concrete, then having a separation for pouring or implementation stage, it is difficult. So for those reasons, we are considering this kind of solution. So it is an optimized way of using advanced concrete material. So it is the same as you suggested. We are using a better concrete mix, but in an optimized way only at the surface. And this kind of idea is actually tested for the beams in putting SSCC at the critical section where there is cracking. And people have observed that this SSCC actually as a cover helps in reducing or bridging those gaps. So this will be like a surface protective layer only, and it will prevent the exposure of the cracks to the environment so that detritus agent cannot ingress, and the durability is somewhat not impacted much.
Okay, I'm looking forward to read more work on this. Thank you.
And I'm going to respond to that part you asked Dr. Dasuki about having an end block. We did discuss that with precasters, and they use it sometimes for post-tension applications, but they really do not like it for pre-tension because it's such an efficient and fast process that changing the form there, because they cast these 3 beams at a time, is not, they don't like it. So, but it would have helped if you could make one rectangular block at the end.
Thank you.
Any other question? Yes, go ahead.
I had a question. Now that you have a 3D printer up and running, have you been able to correlate any of your printed strengths and behaviors with your standardized lab tests? So you have like the direct tension test, flexure and stuff like that. Have you correlated the printed versus your like ASTM standard tests?
So the testing of 3D printed concrete, right? You are asking about testing of 3D printed concrete.
Correct.
Yeah, so we are working on that. We have started to 3D print the material, and we are curing that, and it will be done in coming weeks. So we have not actually done a comparative test between how it is different for casted concrete and the 3D printed concrete. So that is our future work in coming weeks.
Thank you.
Pranay, I have one question. Very nice presentation, very interesting topic. Maybe that's something you're really looking into, but I just, it came to my mind to ask you this anyways. Have you thought of the interface between your shell and the normal concrete, and how this really could be a vulnerable and weak link where water could intrude into this crack? You can think of it as a crack unless you just somehow handle it differently. So what are your thoughts on this interface there?
Yes, so that is a problem in these kind of system where we have a coating over the conventional concrete, and we have to still study this aspect, the delamination and debonding. However, from the literature, we have seen that this concrete to concrete bonding, these are good enough for the transfer of those strengths. But this is a matter of investigation for the future study. Yeah.
Okay. All right. Thank you.
So we can also implement some measures to improve the bonding, like 3D printing the cells with some kind of grooves or some rough surface. So yeah, it's still in study, but we are also looking for that as well. That is in our scope also.
What I meant specifically, and maybe that also what you have been, what your answer means, is that the interface when your end region ends, and now you start actually placing your normal concrete, not the interface between the, the concrete and the pre-printed concrete at the end region, but, the interface between the end region and the non-end region phase. That's going to be the critical part, which is the line shown there in your section. So that's something also maybe that needs to be, yes, exactly that line right there. So that's an interesting thing. I don't know how you can handle a problem like that, and with reinforcement, with what type of material there, transition from non-printed to printed. That's an exciting thing.
Yeah, so like when we will conduct a kind of 4-point bend test with this reinforced beam, we will get answers to some of these problems that may arise.
Sure.
Thank
Looking
you.
forward to that. Sure. Thank you.
I have a few minutes. If any more questions, I can entertain. I think we don't have anybody. So let's go to our next speaker, Professor Jacob Hansen from University of Illinois at Urbana-Champaign. He has a long list of work that he's performing over there. He works in the concrete material and structural engineering area, especially relating to pedagogy. So let's hear from him, and he will be talking on this topic. Okay, go ahead.
Thank you very much. Yeah, so I'm Jacob Henschen. I'm a teaching assistant professor at Illinois, and I'm joined by my colleague and co-PI or PI, and Siktesh, who's an assistant professor in the same department. Our work is on this idea of making camber be an adaptive property in precast concrete sections. This work was inspired by some work at the University of Stuttgart, where they were looking at embedding hydraulic actuators in concrete beams, specifically, or more specifically, not concrete. They were looking at mortar type applications. These were also actively controlled hydraulics, so not really practical when we talk about developing something for like a bridge girder or something that has to be maintained longer term. So as we started to think about this challenge, we just wanted to work through the problem. So if we have a beam, whether it's pre-stressed or not, any type of precast beam, once we remove the pre-stressing, remove the formwork, etc., that kind of just sets our camber, that sets our geometry. This is limiting when we start to talk about things like creep in our pre-stressed beams, what happens when loads begin to change, all these other challenges that may arise during the life of a structure. We aren't really able to adapt concrete to very well. So borrowing from this idea with the active hydraulic actuators, what if we think about maybe using some type of anchor? There's a lot of expansive concrete anchor systems out there that will generate these internal compressive forces in that top layer that can actually start to adjust our camber. These anchors could be something where they are load activated. So you think about a load passing over a bridge, all of a sudden the bridge is actively cambering itself, or it's something that it would be some type of post-installed system. But basically what we're getting at is we will have our beam to deflect, and then we can use some type of system to basically cancel out the deflections. Previously, we've presented on the modeling that goes into this that follows this dynamic relaxation formula. Starting with the strut and tie model, this is a static analysis where we solve for nodal displacements, element forces, all the usuals. But instead of just having that system that doesn't move, we add in this actuator element that has an infinite stiffness, and then it also then is able to move and change the geometry. With this algorithm, it's been around for quite a while, but we've added this folding and bending energy element where at the nodes now, instead of having free rotation, there's rotational springs to add some stiffness as we get the rotation through our structure. So with the modeling in place, then we set out to work on what systems could actually generate this mechanical expansion along the top that would actually impact camber. And we started with just kind of typical concrete anchors. So these are steel sleeves around a bolt with a wedge on the end of it. So as you tighten it, that sleeve expands and bears into the surrounding concrete. They can take a couple different forms. You see on the left, it's just it expands at the bottom. The ones on the right expand through the center. And then we also thought, well, okay, let's maybe work on a more idealized system too. So we actually just employed this lab jack where then we can control exactly the displacement at the top. It's actually pretty challenging to measure what is the force in these different anchoring systems. With the lab jack, I'm going to talk about how we kind of calibrated that a little bit in a few slides. But with a lot of those anchors, we had to kind of get creative. So we were working with some scales and kind of some jigs to understand a little bit as you start to actuate these anchors, what is that expansive force? There's a lot of elasticity built into the system as you tighten it. So it's a little bit difficult to get a real, reliable correlation between maybe how much you tighten the anchor and the force it is exerting on the material around it. So we started with kind of the lab and these jigs, and we quickly realized we needed to move on to just concrete. And with concrete, we use kind of what I've always called my typical concrete. It's a formulation with 0.42 water cement ratio, so it gets us around 4,000 psi. The just using standard lab stands and 3/4 inch nominal maximum size limestone coarse aggregate, very, very standard mixture. This is what Illinois DOT uses for a lot of their pavements and things like that. The only thing we pull out of it was the air entrainment. Now, with that in mind, I did come back and add some fiber reinforcement because as we're starting to create these internal stresses, I didn't want there to be, just a crack and all of a sudden we lose the specimen immediately. I just wanted it to be a little bit easier to work with. So there was roughly 1 pound per cubic yard of polypropylene fibers added to the mixture. Very, very low dosage, only meant to kind of hold things together. Some of the specimens we did play around with adding some reinforcement to, really, really small bars, once again, more for crack control than anything else. The beams we cast to test are 4-inch by 4-inch by 16 inches, so they are not quite the standard modulus of rupture beams. We wanted something that would be smaller, so then when we start to add these anchoring systems, we would actually hopefully see their effects a little bit more readily if we don't have such large specimens. And then just standard curing for 28 days to get to the, like I said, that 4,000 PSI mark. With the specimens then, you can see that we created some with notches, and it was just basically a blank that we would insert into the molds during the casting process that was then later removed. The specimens after casting, we use surface mounted strain gauges with them. And I've done this numerous times where you apply a thin layer of epoxy. That's why the surface looks wet there. And then we apply our strain gauge on top of the epoxy. The epoxy gives us a nice flat, consistent surface to bond our gauge to. And then we can also use just the standard cyanoacrylate cement to fix the gauge. For the most part, we use the larger gauges. These are our 30 millimeter gauge length strain gauges from TML. The longer length really helps with getting more of an average strain reading over that distance, especially since we were using standard large coarse aggregate. Then if we get a coarse aggregate near the surface, then we don't get some weird readings. Although we did use some basically 1/4-inch strain gauges, which are more of what you would expect to be a standard strain gauge. We use those in addition to the longer gauges, just to kind of help provide a little bit more confidence in our measurements. Now, that mechanical jack, and that's where I'm going to start with our results. This is a displacement type device. So it's just a lab stage with a screw that as you turn the screw, it lifts the stage. That's really nice because it gives us a very consistent displacement that we can impose. However, we don't have the ability to then also measure the load in that. And so what we did is we took it to a load frame with a calibrated load cell, and then basically set the height to that opening within our concrete beam. And so then we built kind of our own custom calibration curve with the position of our turning screw and the corresponding applied load. And so we were able to get several measurement points that we had good confidence between applying 0 load all the way up to about 90 pounds. So starting from the theoretical, I just said we can go up to about 90 pounds. Well, this lab jack was only actually rated up to about 22 pounds for general lab usage. So we were actually taking it well beyond its recommended limits. So doing some calculations, what does that 22 pounds get us? Well, it gets us about 2 microstrain right at the top surface of the beam. This 2 microstrain actually does work out to be basically give us plenty of camber to cancel out any deflections due to self-weight. Obviously, if we start to apply loads, then we'll have to apply a lot more load to account for that. But at least with the self-weight, we found that, okay, this could, 22 pounds could more than take care of it. So we applied strain gauges right at that top surface where we would expect to see about 2 microstrain. And then we also applied it on the 2 gauges on the side to get kind of the top and bottom where you would hope that, okay, maybe these are going to be equal and opposite. So then what does the experiment look like? Using that jack, then we were able to apply the load basically up and down, and we did that several times within that kind of calibrated spot between 0 and 90 pounds. And this is what the results kind of showed is, okay, we kind of see what we expect. There's probably some seating loads in or seating behavior within the jack, so we maybe don't see the nice linear trend that we would expect. However, as we think about that calculation of, okay, if we apply 22 pounds, we should see about 2 microstrain. Well, we saw about 0.9 microstrain. When you start to consider that, well, these strain gauges really are limited to about a microstrain for accuracy, the agreement is not too bad in this particular case. So that showed us, okay, well, we're picking up and seeing what we expect at kind of these lower loads in a controlled setting with this lab jack. And so then let's go to our anchors, where again, it's really difficult to actually back out what is that expansive force as you tighten the anchor. And so we use 2 different types of anchor, or 2 different sizes of anchors. They really are the same type. They're these wedge shaped anchors that in the middle there, that picture kind of shows you the force they're exerting on the surrounding concrete. And for this, we started with just a gauge on the top and the bottom, where that top gauge was going to be kind of right where that bell flaring would be for our anchors. With the smaller anchors, we could pretty easily get them in a line of about 3 across the surface. Again, remember, this is a 4-inch wide member, so getting 3 in there is probably, we really started to see problems if we tried to get a 4th one in there. So we limited it to 3 with the 1/4-inch anchors and 2 with the 3/8-inch anchors. So then we went ahead and started to apply our loads. Again, this was, now we're not working on the notch beam. We're working on one that is just a regular prism. And this is what the results showed for the 1/4-inch anchors. With these 1/4-inch anchors, they are built to be lower load. And so we saw that they don't generate nearly as much stress. They don't generate nearly as much stress that we maybe need to see. I highlighted here the 10 microstrain level, because that's about where that 90-pound actuator force, or that stage was able to achieve. Now, again, because we don't have a real great understanding of the correlation between the level of expansion and how much the anchor is deforming as you tighten it, this is where I wanted to highlight these forces, because you'll note that on the bottom axis of this is not a specific force. It's what we were doing is we were doing specific turns within our anchors. Now, with these smaller anchors, we also noted that the sleeves had more deformation when we were applying the load. So that really pushed us to think, okay, we should go ahead and take a look at the larger anchors because the metal was several hundreds thicker. So we were hoping that we would be able to generate more stress, even though we were only using 2 anchors as opposed to 3. So we did this single row of 2 anchors, and then we also started to add strain gauges to see, okay, can we actually can we prove that, you know, plane sections remain plane? What's the behavior like? And for the most part, things looked pretty good from the data. We're still working on this. We're still kind of calibrating some things. With this particular specimen, I think with all the anchors, we embedded them 1 inch below the surface, with the top strain gauge being at 1/2 inch. Again, trying to get that strain gauge to be kind of right where we would expect that maximum amount of expansion from our anchors. Well, I think we probably went too low with the anchors, or we need to move that upper strain gauge down. As you can see from the orange triangles there, it kind of just hovers around 0 strain, where the others actually are taking off. Now, what is kind of interesting is, well, that middle lower gauge actually is experiencing tension all the way through. So we're actually, you know, we're not in a nice linear elastic region, but this warrants a little bit more investigation. So far, we've really kind of done a lot of work with understanding, okay, how do these anchors work? What types of stresses, strains can we generate from them? We've begun to correlate the results with the lab stage or jack that we have been using. And we've found that, okay, so two of the larger anchors, 3 of the smaller anchors, we're seeing about the same or even more stress generated than what we could with that stage, which is exactly what we want. We want to be able to go to these anchors and use the anchors, so then we can start to apply them over a larger surface of the beam. So we're going to continue to look at, we're going to maybe try some even larger anchors, start to look at additional basically anchors. So far all we've been looking at is, you know, a single row with measuring the strain right under it. Well, let's start to look at more rows. And so then we can actually see how much additional stress we can generate from those anchors. And then we'll also start to measure and correlate those camber measurements. We haven't been measuring camber because we just want to try to understand the stresses that are being generated first. We'll come back and get the camber measurements later. And then finally, we are ready to start working on larger concrete sections. So as I said, we're on these 4x4 by 16 beams. Well, it's very easy to go up to the 6x6 by 20 MOR beams. And then we'll continue to get larger from there. And so with that, welcome any questions. I want to be sure to acknowledge TRANS-IPIC for the funding to support this. We've been able to support several undergrads. So George, Faisal, and Calvin are undergrad students, and then Michael and Abdul are master students that have been involved in this work at different points in time. So thank you very much for your attention. And again, I'll welcome any questions.
Any question? No question.
Well, Jacob, very interesting presentation and topic, and very exciting, really, to see the work coming along. I know it's a tough topic. It's not an easy or straightforward, idea that you guys are trying to pursue here. In your first slide, maybe first or second, you showed kind of your idea with a schematic where you have like these internal voids where you can place the anchors inside. Now, the anchors you showed today, they are actually protruded outside of the section, so they basically would interfere with, of course, any other components or pavement placed on the top of it, assuming that's a bridge girder, for example. So what are your thoughts on the practicality of having these voids and you placing the mechanical anchors inside of them in real life, beams?
Yeah, so that's a really good question. And it's something we're going to have to look at. If this was something that, as we think about if this is going in a bridge girder, is it okay to leave those protrusions because you're going to cast a slab on top of it, and then it'll actually help with shear transfer between the slab and the girder? But then it also eliminates any possibility for modifying them later. And again, that's where we're hoping that these are adaptive, not just static devices. That's a really good question. And it's something, we've been talking about and trying to brainstorm. What would these actually look like in practice? For now, we're focusing on, will this concept even work? Because then we can really dig in on what's the optimal type of anchor actuation system to actually generate appreciable forces and to accurately control the camber, because obviously you don't want to all of a sudden fracture your beam because you over cambered it, or all these little discontinuities cause premature deterioration or things like that. So,
Right.
Yep.
No, I agree. So you guys are in the stage of like proofing the concept still, right? Very early
Yeah.
stage. Okay.
Yeah.
Thank you.
Any other question? It means the speaker has done excellent job. No further question. Okay, thank you. These are the 3 presentation for today. Thanks all the speakers and the participating schools. Also, thanks to the audience for patiently listening. I feel it has been a nice afternoon to learn from each other on different topics, and we can expand our knowledge the way we want in any directions. And if any feedback is needed, you can contact the speakers. I am talking on behalf of them. And with that, I'm just also thanking the Board of Regents and TRANS-IPIC Center, and especially to Dr. Basemandus, who is leading the whole thing, whole run. Anyway, with these things, I'm rolling it to Dr. Basem or Chris.
Well, thank you, Baba, so much. Really a great job. As you said, echo what you just said. It's an exciting thing to see the work progressing, and again, I just would like to say that this center is not possible without the effort of every single researcher, PI, co-PI, students, and I think everybody's doing their job perfectly, and I really appreciate that, and looking forward to more and more working with you all. Thank you so much. And as I said earlier today at the beginning, the RFP went out, so please start forming teams, thinking about, new research ideas, or if you want to continue in the same direction of research, also that's a possibility that we are offering, obviously, for the second year. So we will be the leadership team, the associate directors, and myself will be meeting hopefully in the near future to discuss, the RFP. If you have any questions, any of the faculty here with questions, please reach out either to your associate director from your institution, or to me, or of course to Chris Lockwood, who's also I'd like to thank for the great coordination of this, webinar and all the efforts that our center is doing. Thank you all so much, and I hope you all have a wonderful rest of the afternoon. Thank you. Bye-bye.
I have a question, Vasant.
Yeah, bye-bye.
Do we need to get the feedback from our all research participant in the project for the upcoming RFP? It has come.
You don't. No, each associate director will work with the team the way they wish. I mean, the way they want. I mean, you want to hold meetings individually with them, that's fine. If they reach out to you, you want to have a meeting with us, including them in these meetings, so you can coordinate that as well. So really, each associate director will have that, the way they want it. So, but for now, we're gonna hold like an associate director meetings with me, and then we'll see where to go from there. And Chris will be reaching out to you all to check your availability for that upcoming meeting.
Okay.
All right. Thank you all. Take
Thank
care.
you.
Bye.
Thanks, everybody.
Thank
Bye.
you. You did
Bye-bye.
great job.